So if you just bear with me for a minute. Thanks for getting your assignments in. That's been really good. I'll try and get them back to you by about next Monday, all being well. That's the plan. What are we doing today? Oh, that's right. Oh, yeah, so last week we were looking at the exponential and logarithms, and the idea is that functions that look like an exponential, like 2 to the x, grow much more rapidly than polynomials or power functions like x to the 3. And they grow in turn much more rapidly than logarithms, so log of x. And so if you think of a hierarchy of exponentials, powers, and logarithms, logarithms are the most slowly growing. They grow, but very, very slowly. Powers grow more quickly, but not as quickly as exponentials. And just to go back to the situation with this virus, what all the policies have been in place is trying to limit what would ordinarily be an exponential growth. So if you think about one person infects 2 others, so after the first, you've got one person infected. After 1 day, 2 people are infected, and then 4, and then 8, and then 16, and then 32, and then what happens after 32? 64, 128, 256. And this exponential growth means that very rapidly and very quickly, more people will be infected than the system can handle. So everything's been, all the policies have been revolving around trying to limit that exponential growth, this so-called flattening of the curve. So the curve is actually the exponential curve. And what they would like to see is something that's not exponential. Okay. The other thing that I need to mention too is that, is everybody aware that next Monday is a university holiday?
Yep.
Okay. No, right. Thumbs up if you knew, thumbs down if you didn't. Thumbs up if you're really happy that Monday is a university holiday. So it's to do with Anzac Day, of course, that Anzac Day falls on Saturday. And so because of that, the university gets a day in lieu of something somewhere else. Right. Okay, so just going to rearrange things here a bit. Okay, let me see, what am I doing here? That. Okay. So, as I said, we did exponentials and compared to powers, compared to logarithms. And I said last time that we met that, in fact, this week's work, or this lecture's work, in a sense is more interesting because we're starting to look at complexities of algorithms. So basically, how long does an algorithm take to run? So the one that we're going to look at today will be largely to do with sorting. So sorting is one of those things that is a very frequent application in computing. So if you've got an Excel file, sorting by ID number or name or address or first name or last name or ID number, we're sorting things all the time. And I asked you, I think last time, to think about how you might go about sorting something. So you've got a pack of cards in random order. How would you sort them into an ordinary into by suits and then by suits and then by rank within the suit. I've just lost a bit of space here. Okay, so bearing that in mind, that's our canonical example. It turns out that some ways of sorting are more efficient than others. And what if we had time this semester, actually, I'd do a lot about sorting, or a lot more algorithms. Let's dive in and see what's happening. Now, if I share with you, right. I have to say I much prefer a live lecture, or at least a lecture with, I think, with everybody in the room. I'll wake up. And here we go. Right. Just okay. So what we're doing is this thing called time complexity. So complexity is really just a fancy way of saying how much time does it take for an algorithm to run given the size of the input. So broadly speaking, if you've got 10 cards or 10 names to sort into order, how long does it take? Or more importantly, if you have 100 cards, so you go from 10 to 100, how much more time does it take? So you can think that going from 10 to 100, maybe it takes 10 times as long. That would be quite a reasonable expectation. But some algorithms, suppose you went from 10 names to 20 names, instead of taking twice as long, some algorithms might take 4 times as long, which is really quite surprising. So there are some tasks where doubling the size of the input requires more than double the amount of time to actually implement. Thankfully, sorting isn't one of those. In fact, sorting is one of the problems where there are algorithms where if you double the size of the input, there's a list of names, then the amount of time is maybe only 1.5 times as much. So it's a bit, which is really quite surprising. Anyway, so let's go into here and that. So basically, we're not really interested in exact numbers. So, when I say we've got a list of 1,000 names to sort, we're not really interested in that it will take 2.17956 seconds. What we're really interested in is how much time it takes relative, in say doubling the size, or in orders of magnitude. So when we talk about orders of magnitude, the idea is something like, if I say it takes 140 steps to perform a particular algorithm, or 157 steps, I'm not really interested in the difference between 140 and 157. It's about 100, okay, or about 200. Or if I say, I've got an algorithm that works in 100 or 200 steps versus something that takes 1 or 2,000, then the order of magnitude is to do with how many hundreds, so the hundreds versus the thousands. So I don't really care that it's 100 or 200 versus 3,000 or 4,000. What I'm really interested in is it's 100 versus 1,000. So some multiple of 100 versus some multiple of 1,000. So 15 operations or 25 operations, look, you know, these are just so fast, we won't notice a difference. In fact, it's almost impossible to time it. But if there are 15 versus 15,000, you really want to be steps. You really want to be concerned with the efficiency. So a way of describing this is this big O notation. This is a letter O, not zero. So big O means that we're using roughly n operations where the size of the problem is n inputs. So you think of n names in a list. So if you have 100 names, n will be 100. If you've got 1 million names, n will be 1 million. In case you're wondering about, I say 1 million, there are some problems that actually you measure the input in terms of hundreds of millions, if not billions. And in those cases, there is serious computational issues. So if you can reduce the speed of the complexity, the number of steps in the algorithm, you're going to be saving, not seconds of time, but hours or days or even weeks worth of time in running the thing. So this, I don't know if any of you ever go hiking or even around the streets of Bendigo or Melbourne, you'll see little, I'll go back to stop sharing there. Sorry, come back in. So if you go around the streets in Bendigo or Melbourne, or you go hiking, you'll see these little metal discs embedded into the pavement, about yay big. Some of those are what are called trig markers used by surveyors, and the idea is that you can triangulate and get an accurate physical location, so longitude and latitude from a whole system of these. Juggling two screens. There's a share screen. Now I've lost. Sorry, I've lost her. Oh, there we go. Okay, so the idea is that you've got a system of these trig markers. One might be at the top of the hill. If you've seen some hills, they've got a white pyramid triangular frame at the top. If you've ever wondered what those are, they're surveyors' markers. And so the idea is that you've got a system of these and you can triangulate. So you're sitting here and you look at, you can't see that. You're sitting here and you point your theodolite over to here and over to here, and you work out the angle between them, and you also work out the distance between them. Then you go to here and you point your theodolite there and there, you work out the angle, you work out the distance, and you come down here, you point your theodolite there and there, you work out the angle, you work out the distance, and from that you can work out, if you know this accurately, then you can work out where the others are. But it turns out that when we do this, I think in the United States, there's about 1 million of these points. And you have to solve big equations with millions of variables to figure out the precise locations. And the problem there is that is computationally an enormous problem. So any method that you can use to reduce the number of steps really is just extraordinarily useful. As I said, the savings is measured in days, not seconds. So that's your cultural enrichment for today. So we better get on to this. So the idea here is that what we're meaning here by big O of n squared means that we don't really care if, so n is the size of the input. We don't care here if it takes 2n operations or 100n operations or 7n operations or even 6n plus 4. So an algorithm might take, one algorithm might take 2n operations where n is the number of inputs. One operation might be 100n, another one might be 6n plus 1. They're all roughly the same order of magnitude. They're all just a multiple of n. So that's really what we're saying with that big O. Compared to something that takes n squared plus 2n plus 3 operations. Okay, so the biggest thing there is n squared. That's going to be what dominates. So if you've got 100, the size of the input is 100, then the 100 squared is much, much bigger than the 200 there. And what you're interested in is really the 100 squared. Or your algorithm might be 4n squared minus 6n. Again, the thing that dominates in the count of it is the n squared. So this is what this is really meaning. So here we've got a calculation. We're looking at 3 plus 2 plus 4 plus 5. It's got 1, 2, 3, 4 inputs. And how many operations are required? Well, there's 1, 2, 3 additions. And in general, if you're on the list, add a list of numbers where you've got n numbers in the list, then how many operations are you going to do? Well, one less than the number of things that you have to add up. And so if you think about it, if you've got 100 numbers to add up, how many operations? 99. If you've got 1,000 things to add up, how many operations? 999. There's not really a lot of difference between 199 or 100 and 999. So that, in terms of the things, we may as well describe and say, well, instead of 999 operations, it's about 1,000. Instead of 99 operations, it's about 100. So this is what this is saying here. This subtract 1 is really insignificant. So even though the exact number of operations is, if n things, n minus 1 additions, that's just so close to n, we may as well say it is n, and that's why we talk about order of n. So here, with this one, you've got 3 different programs to do the same thing. It could be sorting. One takes order of n operations, one takes order of n squared operations, and one takes order of log of n operations, so log base 10. It actually doesn't matter really what the base is. But so with 1 million inputs, okay, how long would it take to run each of those? Okay, so with 1 million inputs, what's a logarithm of 1 million? Log of 1 million is, in base 10, basically 6. So let's pretend this is a really, really slow computer. So 1 microsecond, that's 1 million operations a second. How long will it take? 6 microseconds. Okay, the second program, so we've done this one. The second program takes ON operations. So about how many? Well, basically about 1,000,000. So how many, and if you're operating at 1,000,000 operations a second, then it will take 1 second. Okay, so you can see that this one is much faster than that one. I mean, 6 microseconds is way, way smaller than 1 second. So the log, the order log, is saying that this is basically a more efficient algorithm. On the other hand, if you go to the order n squared algorithm, how long will it take? So remember, we had 6 microseconds, 1 second. How long will this algorithm take? Well, n squared, 1,000,000 squared is 10 to the 6 to the 2, or squared, that's 10 to the 12. And that's how many operations are required. How many seconds is that if you're doing 1,000,000 operations a second? 10 to the 12 divided by 10 to the 6 is 10 to the 6. 1,000,000 seconds. How much is 1,000,000 seconds? Divide by 60 to convert into minutes, divide by 60 to convert into hours. You get 278 hours, about 11 and a half days. So that's, so you can see there's a huge difference between, a minute fraction of a second, 1 second, and 11 and a half days. So if your algorithm, if you're choosing between these algorithms, which one do you want? Well, clearly the most efficient, the log n algorithm. So we get to this idea of if an algorithm runs that quickly, in other words, if an algorithm uses so few steps, that's really what it's about. You're counting the number of steps. And the fewer the steps involved, the more quickly it runs on any computer. So if you've got an algorithm that has this order log n complexity, or any power of n, with realistically sized input, so n is equal to 1,000,000 is actually nowadays not an unrealistic thing. If you think 11 and a half days is long, well, yes, it is, but there are algorithms out there, real world things that are solved, I won't say every day, but real world things that are solved that actually do take, on the order of weeks to solve. So if you've got an algorithm that has this order of complexity log n, or n to some power, on a reasonably powerful machine, the execution time isn't going to be so bad. So we talk about these as being a tractable algorithm. But if you've got an exponential, order the 2n, or order to the 10n, the execution time just grows so big. I mean, it's this idea that we've been looking at. Here's n squared, but here's 2 to the n. It's just for a small increase in the size of the complexity, the number of inputs, the time involved, or the time increase is just enormous. Sorry, just have a look there. Yep. So these are really bad algorithms in the sense of how much time they take. Unfortunately, there are some problems where that's the best that we know, and that we don't know of any faster algorithm. So then we talk about this idea of tractability. So an algorithm is tractable if its time complexity, the number of operations, is basically a power or a log. And it's not tractable if it's an exponential of some sort. Okay, so here an algorithm has time complexity log n. Is it tractable or intractable? Well, log n is much less, grows more slowly than powers, and powers are considered to be tractable, so log is considered to be tractable. So if you say to me, your algorithm runs in 5 log n operations, I'll say that's a tractable algorithm. Okay, so insertion sort algorithm. So this is just one version of sorting. There are a whole lot of others. There's something called the bubble sort. There's insertion sort. There's something called a heap sort, and what's the other common one? Insertion sort, heap sort, merge sort. Yeah. Insertion sort, bubble sort, merge sort are kind of obvious. Heap sort is really, really interesting. I don't know if we'll have time to do this semester, but it looks totally unlike what you'd actually think up yourself in terms of here's a deck of cards and let's try and sort them. It runs very, very quickly in comparison to most sorting algorithms. Anyway, so insertion sort. We've got a list of numbers and we want to put them in order from smallest to largest. So we'll just go small to big. Okay, so the idea is that we divide we've got our list of numbers, and we're basically going to divide it into two. The bit that's already sorted and the bit that remains to be sorted. And the way we do it is this. So first of all, let's just put the dividing line between the first two. So this is the sorted list, and this is unsorted, basically from what we started with. Now, so we take the leftmost number in the unsorted list. So here's the unsorted thing. What's the leftmost one? Well, that's a 7. Thankful for the mute button. We look at that, and we're going to compare this number in the unsorted list with this first number in the sorted list. And we see that 7 is actually bigger than 5. So we put 7 to the right of 5 in its obvious place. Now it's clear now that 5, 7 is actually sorted. We've increased this by 1, and we've decreased this unsorted list by 1. And now we do the same thing. Basically, we look at 0, and we compare it with each of these in turn to figure out where 0 goes. So that's why it's called an insertion sort. At each step, we're inserting the next thing in the unsorted list into its correct place in the sorted list. And by the end, we'll have nothing in the unsorted list and everything in the sorted list. Okay, so we had 5, 7, 0, something, something, something. So leftmost number in the unsorted section, where should it be placed in the sorted section? So we move, it doesn't really matter whether you go from left to right or right to left. In this case, I think we're comparing this from right to left to figure out where it goes. So you ask yourself, is 0 bigger than or less than 7? So maybe say, is it less than? So is it less than 7? Yes, it is. So we go back to here. Is it less than 5? Yes, it is. So we go back to here. And at this stage, there's nothing else to compare it with. So we know that 0 has to go just before 5. Okay? So this is where we get to 057, and now we've got the rest. Notice that at that step, we made 2 comparisons. So the idea in the sorting thing is that when we're adding a list of numbers, 3 plus 7 plus 6 plus 3 plus 7 plus 6 plus 5, if you've got 4 numbers to add them up, you need 3 additions, 3 things to do. When we're sorting, we're making comparisons. So we're actually going to count the comparisons. They're the bits that we're doing at each step. So there are 2 comparisons. First of all, we compared 0 with 7, and then we compared 0 with 5. So keep a note there. Actually, we should have kept a note back here. Right. Should have kept a note back here, because when we did 7 and figured out where it went, we had to compare it with 5. So actually there was 1 comparison there. In this one, we had to make 2 comparisons. Okay, next step, 3. 3 you compare with 7, that's 1 comparison. It's less than 7. Is 3 less than 5? Yes, it is. That's 2 comparisons. Is 3 less than 0? Now, notice we actually had to compare it. Is 3 less than 7? Yep. Is 3 less than 5? Yes. Is 3 less than 0? No. So we know that 3 fits in between 0 and 5. So there were 3 comparisons there. The other thing to point out is that, remember, this is, you're going to get a computer to do this. And unlike a human, I mean, as a human, you just look at it and you say, oh, 3 obviously fits in there. But you gloss over the fact that you actually have made the comparisons. Lightningly quick, but you've actually had to, even though you didn't consciously think, oh, does 3 go between here, is 3 here or here or here, you just look at it and you say, oh, I know 3 is between 0 and 5, but that's because you've sort of got it hardwired into you about the comparisons. When you get a computer to do this, you actually have to tell the computer, compare 3 with 7, then 3 with 5, then 3 with 0. And since it's less than 5 but bigger than 0, you know it has to fit in there, or the computer knows it fits in there. Okay, well, you just basically keep going. So now with 4, okay, so we compare 4 with 7, that's 1. 4 with 5, that's 2. 4 with 3, that's 3. And those last 2 comparisons tell us that 4 goes in there. So we had 3 comparisons at that stage. Okay, then we go to 2. 2 with 7, 2 with 5, 2 with 4, 2 with 3, 2 with 0. So it's 1, 2, 3, 4, 5 comparisons. Okay, finally, almost finally. 6 with 7, 1. With 5, 2. That tells us 6 goes in there. So we actually only needed 2 comparisons. Last one. 1 with 7, 1 with 6, 1 with 5, 1 with 4, 1 with 3, 1 with 2, 1 with 0. So we know that 1 goes in there. 1, 2, 3, 4, 5, 6, 7 comparisons. And we've got our final list in what is the obvious order. And we could actually count up. So here's a brief summary table. Here's our initial list. Here's the actual number of comparisons that we made for this particular list. So we actually